Going to continue on in 3-1, which was our section on solving systems of equations. We're going to do the second part of these notes. We're starting on page 138 in your textbook today. And I'm not going to write down the first part of this, but this is something that you need to know, and it's these characteristics of linear systems. So what happens when we have two lines, there's basically three things total that could ever happen. You can just have your lines intersect. Now, they may not always intersect right there, but they can intersect one time or where there's one solution, all right? If it asks you to classify that system, that's known as consistent and independent, all right? So again, you'll see this on a ConnectEd assignment and eventually on a Chapter 3 test to maybe solve. Last time in 3-1, we looked at graphing two lines and finding where they intersect, but then you classify that and you call that consistent and independent. If you ever graph two lines, maybe they look different at the start. There were some numbers that looked like they were different, but you go to graph and realize that it's the same line, that the slope is the same and the y-intercept is the same. That has an infinite number of solutions. In fact, it's every solution where, for ordered pair that fit on that line. We classify that as consistent and dependent. So you can see the difference in what happened in the first one and the second one, all right? The third one that we have is parallel lines. So if you're graphing these and you realize that the slopes are the same but the y-intercepts are different, we're never going to have a solution. Solutions for systems of equations come from where the lines cross. Or if it's the same line, they cross the whole time. Well, here, parallel lines never cross. It's no solution. We call that inconsistent. So the three classifications are consistent and independent. That's one intersection. Consistent and dependent, same line. Inconsistent, which is parallel line. So I didn't write that down, but you need that table at the top of page 138. All right, let's go to a couple of other ways that we can solve systems of equations, and we're going to do substitution. All right, I'm going to go ahead and jump to the top of page 139, and I'm going to do 4a. So here's what's going on. They give us two linear equations, 5x minus 3y equals 23, and 2x plus y equals 7, all right? We're still trying to find the spot where these two lines intersect, and so you could graph them like you learned in the first part of 3-1, but what I want to make sure that we know, mathematically, there's some interesting concepts with substitution and in a minute elimination that are good for you algebraically. All right. So here's when I might use substitution. So what we want to do is we want to isolate one of the four variables we have. Now we've got two x's and two y's for a total of four variables. I like to use the one that has a coefficient of 1 and use substitution to solve it. So here's what we're going to do. In this second equation right here, I'm going to go get y by itself. Now you can do this for any variable, but when the coefficient is 1, if there weren't any fractions in the problem, there aren't going to be any. So it kind of is clean in its own right. So I'm going to come over here. I've got 2x plus y equals 7. And I'm going to solve for y. Well, you know how to do that. We do PEMDAS backwards, meaning I need to move the 2x. How do I move positive 2x? I subtract it, all right, from both sides. And I get this. Y equals negative 2x plus 7. I'm writing in slope-intercept form. Slope of negative 2, y-intercept of 7. All right, so if I can solve and make this y equal negative 2x plus 7, I can also make that y equal negative 2x plus 7. So I know that's a little bit tricky, but I want you to see. So let me write the top line again. So I'm going to go sub in this value into the line that I haven't used yet. So I've got 5x minus 3y equals 23, and instead of leaving that as a y, I'm going to plug in negative 2x plus 7 for that y. What that's going to do is make it to where there's only one different variable, which is x in the problem, and then we can solve for one variable. So watch what I do here. 5x minus 3, again, times y, but we found what y is equal to in this problem. It's equal to negative 2x plus 7, so I'm going to plug that in, negative 2x plus 7. Catch what just happened. Negative 3 times y, this is negative 3 times y. We just happen to solve for what y is. Y is negative 2x plus 7. I plug it in, and the rest of the problem is equals 23. So take a look at these two right here and see the difference. Y equals negative 2x plus 7. It's a lot, that function notation that y'all been working on where you had like f of 3 and you went and took that 3 and plugged it in for x. Exact same concept, just looks a little bit different on this one. All right, so I'm going to get x by itself, but to do that, I need to do order of operations, meaning I need to go multiply that negative 3 or distribute it. So I have 5x, negative 3 times 2x is positive 6x, negative 3 times positive 7 is negative 21, and that equals 23. I'm not ready to move anything yet because I've got like terms over here. So that's the addition part of PEMDAS. 5x and 6x makes 11x. Minus 21 equals 23. Now we solve for x. Now, as we isolate them, once we get to where there's only one variable, now we isolate it by PEMDAS backwards. I need to move negative 21, so I add 21 to both sides. I get 11x equals 44. All right, if you don't like the math, just do 23 plus 21 in your calculator. To get rid of this 11 times x, I divide by 11. And I get that x equals 4. There is the x value for our system of equations, but that's not the answer. If you remember from the first part of 3-1, we have an x and a y. We have an ordered pair. So I now need to plug in. You can go back to the original and plug 4 in for x. Since we had already kind of solved for y, I think it's easier to come right here and plug it in. So I'm going to bring that down and go y equals negative 2 times x, which is 4 plus. That's just substitution again. This time, the only thing we were subbing in was 4. So it's a little bit tougher to see substitution up here, but the same thing's happening here. I'm plugging in what I know my x to be. Now I finish the math, okay? So y equals negative 2 times 4 is negative 8 plus 7. I did the times first because multiplication before addition. And negative 8 plus 7 is negative 1. Now I have my ordered pair answer. Write it out. X is 4, y is negative 1. That is the ordered pair where those two lines intersect. If you would have gotten y equals in both of these and graphed them, they would have intersected at 4, negative 1. All right, everybody kind of see that? A little bit tricky, but there's some really good math stuff happening there, and we need to practice. All right, I'm going to go to example 4b because, and I want to do another substitution, I want to solve for x now and show you that it works the same way. So I've got x minus 7y equals 11, and 5x plus 4y equals negative 23. Again, I'm at the top of page 139 in your textbook. They're going to tell you use substitution, use elimination. I don't really care, but I want to show you how to substitute, and I like substituting with a coefficient that is 1. Okay? Let me jump ahead in 4c right here. You could also substitute and solve for that y. Just understand at the end you got to divide by negative 1, which is no big deal. The signs are going to change. So when the coefficient's 1 or negative 1, substitution's pretty easy. So I'm going to come over here and I'm going to get x by itself. So x minus 7y equals 11. I'm isolating x, so I'm going to add 7y to both sides, and I get x equals 7y plus 11. So if I found this x to be 7y plus 11, this x is also 7y plus 11. So I'm going to bring it down like I did up here, so I'll rewrite it. 5x plus 4y equals negative 23, and I am now subbing what I solved x for in. Substitution. I'm going to take all this over here and sub it in for that x. So I have 5 times x, remember what x is now, 7y plus 11, and then plus 4y equals negative 23. Look at these two lines. The only thing that's different, I subbed in 7y plus 11 for x. Now the only different variable down here is y. Once I do PEMDAS, then I can solve for y. I can solve for one variable, makes it easy. All right, PEMDAS says we need to multiply, so let's go distribute this. It's the first thing. 5 times 7y, 35y. 5 times 11, positive 55. And I've got this plus 4y equals negative 23. Not quite ready yet to get y by itself because we're not cleaned up yet. I need to do this. 35y and 4y makes 39y, and then plus 55 equals negative 23. All right, now there's only one different y. Now we PEMDAS backwards. So I need to subtract 55 from both sides. Okay? I get 39y equals, if you're not good at doing minuses, remember, how just in the calculator be? Negative 23 minus 55, we get negative 78. Divide by 39, right? we get y equals negative 2. All right, cleaned up pretty nice. There's the y coordinate of where these lines intersect. Let's go find the x. How can we do it? I like coming to this step, this x equals 7y plus 11, and I like subbing negative 2 back in for y. So I've got x equals 7 times negative 2 plus 11. Keep going. X equals 7 times negative 2 is negative 14 plus 11. Finish the math, and I get x equals negative 3. There's your ordered pair. Write it in the right order. The x was negative 3, the y is negative 2. There is the ordered pair where those two lines intersect using something called substitution. Okay, so I didn't write that. Here it is. Substitution. Okay, that's substitution on this page. Now we're going to go to elimination. Let's jump down to example 5. So elimination works a little bit differently. You start trying to cancel things out, and there's a way or there's a time that I would do this. I'm just going to jump into the one they gave us. So here's example 5, and these are examples of elimination. All right, so here we go. I got two lines. 5x plus 3y equals negative 19. 8x plus 3y equals negative 25. All right, so now what we want to do, y'all remember back in elementary school when you used to add stuff up and it would be like 4 plus 3, and it would look like that. You'd add them vertically and go, oh, 4 plus 3 is 7. You'd have a big old list of them and you'd do it. That's kind of what we're doing here. But we want to make a variable cancel out, because if I can make a variable cancel out, then I can solve for the other one. So that's exactly what we're going to do. So if I go add these vertically right now, we're not in good shape. 5x and 8x makes 13x. 3y and 3y makes 6y. So nothing cancels, but mathematically, is there something I can do to make these cancel? Yeah. Now, to be honest, we could make the x's cancel, but that would need to be 40 and that would need to be negative 40, which would be fine, but I would have to multiply that by 8 and that by negative 5 just to get there. And that's fine, and that's an option. But I think it's easier here if you have numbers that are the same to flip the signs of one and then go cancel it out. So that's exactly what we're going to do. I'm going to multiply this whole top line times negative 1, or by negative 1. So here's what that does, and I'll rewrite it below. That becomes negative 5x minus 3y equals positive 19. All these signs flip when I multiply by negative 1. So kind of avoid this, that top line's not really there anymore, and we're dealing with this system. Okay, let's go add these up vertically now. 8x, and when I say add up, you can't subtract. So 8x minus 5x is 3x. Look what happens to my y's. Plus 3y minus 3y cancels. That's the elimination part. So we're going to use multiplication to help these cancel. I keep doing the math. Negative 25 plus 19, negative 6. Again, if you don't like that math, do it in the calculator. Now look at this. 3x equals negative 6. Yeah, we can do that. Divide by 3, x equals negative 2. You just found the x coordinate of where these lines intersect. That's nice. Well, we need to go find the y. Now your options here are go back to any of these and plug in. Remember the original was 5x plus 3y equals negative 19. 8x plus 3y equals negative 25. That's where this problem started, right there on page 139. I would just pick one of those and plug negative 2 back in. It doesn't matter. I'm just going to go to this top line. So again, I had 5x plus 3y equals negative 19. And I'm going to take my negative 2 that I found for x, and I'm really going to substitute it in. So you got to kind of know substitution for both of these, to be honest with you. Okay? Even in elimination, you still substitute in. All right, here we go. So I have 5 times x. X was negative 2 that we solved for, plus 3y equals negative 19. Keep going. 5 times negative 2 is negative 10, plus 3y equals negative 19. I add 10 to both sides. We're PEMDASing backwards now because we're isolating the variable. I get 3y equals negative 9, divide by 3, and I get that y equals negative 3, right? Negative 9 divided by 3 is negative 3. There's the ordered pair. Here's our x, here's our y. So our answer, negative 2, negative 3, put a box around it. If you would have gotten y by itself and graphed these, that's the intersection. Okay, it's all finding the same thing. There's just some tricks. I like elimination when you have two of the same number and we can just flip one of the signs and go. Now, is it always that easy? No, it's not. Let me see if I can find one where we got to do some multiplication. Okay, all right, we're going to go to example 6, and then I'm going to show you something that happens right here on this too. So example 6, page 140. Example 6, page 140. Part A, all right, let me put that in there. Part A says this: 5x plus 3y equals 52. 15x plus 9y equals 54. Okay? So you're looking at those and going, well, I don't have the same number. Right. I don't think substitution is very easy here because there's no coefficient of 1 or negative 1. So basically what I want to do, I either want to cancel out the x's or the y's here. Well, that's a 5 and a 15 and a 3 and a 9. Those aren't the same, but you know what? Could I turn that into a negative 15 mathematically? Yeah, I could. I multiply by negative 3. Or, hey, I could turn that into a negative 9 to cancel out. So you can cancel out the x's or the y's. Since we canceled out the y's in our first example, let's cancel out the x's. I need to multiply this line by negative 3. Coach, why are you doing that? Well, because negative 3 times 5 is negative 15. And negative 15x will cancel out with that 15x. All right? So here we go. I'm going to do the math and write it underneath. Negative 3 times 5x, negative 15x. Negative 3 times 3y is negative 9y. Negative 3 times 52, I think I know what it is, but I'll double check. Right? Negative 156. Oh, that's a big number. Okay? So now I'm kind of not looking at this top line. So look, our x's cancel out. Awesome. That's exactly what we wanted. They eliminated. So that's normally where we would go, and we'd go solve for y. But guess what happens with our y's? I've got 9y and negative 9y. Uh-oh. This whole side cancels out, and it equals 0. What? And then you do this math out here. Well, you can add those together, and you can go, I can do 54 minus 156, negative 102. What's going on there? Negative 102? You got to ask yourself right now, is that true? Is 0 equal to negative 102? And obviously the answer is no. When this happens, you just had parallel lines, and we have no solution. They don't intersect. So this is a great example of what happens when you try to do elimination, and to be honest, with substitution, you'd come across something similar if the lines were parallel. So parallel lines, you're going to get two numbers that don't equal each other, okay? Now, I'm not going to do example 6b, but I do want to show you what's going on, okay? When they do the math right here in the textbook, they get to this step where they've done all this math, and they get 0 equals 0. And you've got to kind of ask yourself again, hey, is that true? And it is. So up here, it wasn't true. Here, it is true. 0 equals 0. When that happens, you had the same lines. So you have an infinite number of solutions. So you're just going to come put, it's basically every ordered pair that fits on whatever line they gave you. Remember, these are the same lines, so they gave that to us up here in example 6b. It's the same line. So if the ordered pair fits that line, then it's a solution, and that goes on, and that's infinite. It goes on as long as that line goes on, which is forever, okay? There's a lot going on right there. They give you kind of a list of ways that you can solve systems. I'm giving you the green light to solve it however you want, but you need to understand how substitution and elimination work, especially because this isn't your last math class for most of you, and you got to understand how to work some of this stuff by hand, all right? Appreciate you paying attention. As always, please come ask for help if you need any help. Thanks.